Honorable Shaw laureates, distinguished scientists, forum participants, ladies and gentlemen, good morning. Welcome to Day 2 plenary session at the Hong Kong Laureate Forum 2025. This is Patricia Young, and it's my pleasure hosting for you this morning. On behalf of the HKLF, a very warm welcome to all of you joining us in person, and to those of you tuning in via our live webinar. Yesterday, we had a grand opening ceremony and masterclasses on 2 disciplines. I believe those who had attended were excited with the inspirational and intellectual idea exchanges. Today, we're truly honored to have 3 renowned scientists in astronomy and life science and medicine to share with us their knowledge and research experience. This morning, we're privileged to begin with a keynote speech by Professor Reinhard Genzel on massive black holes, experimental evidence, and cosmic evolution. Following that, we'll move into a thought-provoking panel discussion with 2 distinguished scientists, Professor Kazutoshi Mori and Professor Peter Walter. And I'm sure many of you are familiar with Professor Reinhard Genzel. Please allow me to provide a brief introduction. Professor Genzel was awarded a Shaw Prize in the discipline of astronomy in 2008. In recognition of his outstanding contribution in demonstrating that the Milky Way contains a supermassive black hole at its core. And among a lot of other globally renowned prizes he received, he's a Nobel Prize winner in physics in 2020 for his discovery of a supermassive compact object at the center of our galaxy. He's currently the director and scientific member, Max Planck Institute for Extraterrestrial Physics, and the chair of the board of adjudicators of the Shaw Prize. Now, ladies and gentlemen, please put your hands together to welcome Professor Reinhard Genzel.
Good morning. Is it too early? It's too early for me. I go back to bed. Plus, these black holes, who cares? Yeah, well, I mean, that's a question, actually, which many people might ask. Why am I giving this talk? You know, every movie producer knows that black holes exist. So why do we need to make a scientific subject of it? Well, of course, you know, we have these beautiful pictures from the movies and so forth. So there it is. And we know the black hole is supposed to be something black in the center. And then the light emission outside. And we know, we've heard that it's pretty difficult to get out of there. Getting in is easy, but then once you get in, ooh. Okay, well, but I mean the scientific issue, of course, if you listen to any of the many astronomy talks these days, you will encounter black holes as one element quite often, just like exoplanets maybe, or galaxies. So the question physicists, and I consider myself in that sense a physicist, is fine that we think we have these objects where gravity is so strong that light cannot escape, but do they really exist in the sense of physics? So that's what I'm trying to tell you about. Now, if you have listened very carefully, the Nobel Committee wasn't very cautious on this, right? It said, of a very massive object, probably a black hole. So that tells you that the Nobel Committee still leaves some holes open, and we are working extremely hard to close these holes. I would bet you in about 40 years we will really know, but we're not done yet. So let me tell you where we are. Now, of course, as a little background, just for those of you who have not encountered black holes, what are they? Well, mass, we know. We know the mass of the Earth, and we know what gravity is. If I try to jump, despite my bad knee, I will come back down. Every one of you will come back down. You can try it. Now, of course, the faster you jump, the higher you might get. And the physics of Newton tells us that if you take a rocket on the surface of the sun and let it go off the surface at a speed of 600 kilometers per second, roughly, then it will escape. It will escape into distant space. So that's the escape velocity, and that tells you something about the strength of gravity. And the gravity is determined by the mass of the sun, but also its size. So if we go in mind to a different sun, which has the same mass, but is smaller, then we know from physics, gravity is stronger. So if you calculate, according to Newton, the escape speed of that rocket, if it's a 3-kilometer diameter of the mass of the sun, a number comes out which some of you may know, 300,000 kilometers per second. That's the speed of light. And we have very, very firm, absolutely clear evidence since the late 19th century from experiments that there's nothing which can go faster than speed of light, independent of what people tell you. That's all fake news. So, if that is the situation and such an object exists, that means that inside of a characteristic radius given by the mass and size, light cannot exist, cannot escape. Also, masses cannot escape. Now, here's a second aspect which immediately you've learned. I talked about light as if it's particles. And indeed, during the early part of the 20th century, Max Planck and others learned about quanta and learned that photons, particles of light, have an energy, and the energy is equivalent to a mass. E equals mc squared. You may know that equation. So that means once you have such an object with this radius, then neither light nor any particle with a mass can escape. But if you bring it inside, it will fall to the center. And mathematically, that center is a point. So it's a center with infinite density. That's what the theory of general relativity by these men has predicted. A point with infinite density, and all of the energy, mass energy, is contained in this. Now, it took a long time after the publication, so to speak, of Albert Einstein of the theory to be really tested out mathematically in more detail. There is a man named Schwarzschild on the top here who asked the question, well, let's take actually a likely configuration of such a mass, namely a sphere. How would it look then? Others asked the question, what if this thing has a spin, it rotates, what happens then? What if it has a charge? So all of this got investigated in the 50 or 60 years after Einstein's prediction in Berlin 109 years ago. So it took, about 110 years before we can actually talk about experiments. Amazing. Although gravity is very well known to us all. But to learn about gravity is extremely difficult, and that you will see. Now, how can we see gravity if it doesn't emit light? Well, in principle, you do the same as in the solar system. If you had such an object we call a black hole in the center, and you had a bunch of objects with the same mass as the planets around the object. If it has the mass of the sun, well, then they wouldn't move around to first order like planets around the sun. And so that is a way to experimentally infer that there is a central mass. And you can even measure its mass because the exact speed of the orbital motion, remember the Kepler laws for the solar system, tell us how much mass there is in the center. So that's one, obvious way to perhaps, find a black hole. Now, there are other ways, of course, and I will briefly touch on that to do this. But it took 60 years after Einstein before the first real evidence for possible existence of such black holes came to the fore. One was discovery of very bright binaries, one of which was an X-ray star. And then the other one is this one here. Objects which showed up in the radio, were measured in the radio, and then when you look up in the optical, which you see up on the top left, it looks like a star. You see these diffraction spikes. Actually a fairly faint star in this particular case, 16th magnitude, not very bright at all. You can't see that with your eye, but with a big telescope you can. And then and that was done by Martin Schmidt, the man on the left down there, you take an optical spectrum, so you disperse the light, and you see the different colors. You see the very, very, very clear-cut lines in that spectrum. And those lines have ratios of wavelength, which we know very well. And they point to hydrogen, and helium, and neon, and so forth. But they are all redshifted by 16%. Now that is pretty incredible. 16% of the speed of light. So what does that mean? Now the interpretation of the theorists who thought about that at the time, after about 8-10 years of discussion, went towards the expansion of the universe, which was already well known since the 1930s. So this is now 1960, and since 1930, we know the universe is expanding, and in an expanding universe, the further something is away and sends light to us, the more this is redshifted. So if you take that redshift they measured here of 16% and calculate how far away it would be, you come up with a number of 2.4 billion light years. 2.4 billion years of light to get from there to here. Now that at the time sounded outrageous. The universe, which was known then, was millions of light years, not billions. Now, of course, nowadays we know that the universe is 13.7 billion light years old. So this is far away, this object. Now, if it's that far away, then of course what looks like a mega faint star is in reality extremely powerful. So if you can calculate that, then it comes out that this little light point there is 1,000 times more luminous than the entire Milky Way. 1,000 times. And all of this coming from a region which is a mere light year or less across. How can that be? Now, the theorists at the time thought about this for quite a while and then came up with what you might say is an absurd explanation, which is accreting black holes. Oh, you say, that can't be. You told me that light cannot escape from black holes, right? And now you want to tell me that this produces light? How can that be? Well, because I told you that light cannot escape within the event horizon, but outside it can. So if you let a lot of material fall onto a black hole, then you produce a lot of energy, and that energy then can produce light. So that's the proposal. That was the proposal of famous men like Donald Lynden Bell and Martin Rees in Cambridge. and many others, but this is not proof. The proof, of course, is can we actually see that in reality? Now, to do this, we need experiments, and I'll show you 3 experiments which have been participating in the last 50 years to make the case pretty good. One is motions of stars around the center of our Milky Way. The center of our Milky Way is the nearest galaxy, so while quasars are so far away, our Milky Way is a mere 27,000 light years away, so that's around the corner, so to speak. So that you will see was done and how it was done. The next experiment in the end was finished, or at least came to successful results at about the same time as the first experiment, and that's gravitational waves. If you have masses which move very fast, well, then it generates changes in the space-time curvature, and that you can sense through gravitational waves. And then finally, you can actually go ahead and use what is known since a long time, a radio interferometry, where you take radio telescopes over the entire globe and measure the light which comes from a distant point and interfere the light. I'll say a little more about this later. Interfere the light, not just detect it, but interfere it, and thereby generate what is the size of a telescope equivalent to the size of the Earth. And that gives you enormous resolution. And that was also a very important part of the success of the last few years. So let's say a little bit more about the technology. Now, I won't go into too much detail, but of course the first thing is we need resolution. These black holes are very, very small. If you take the mass of the Earth as an example, then the event horizon size of the Earth would be 1 centimeter. Now put that far away and you can immediately see that object is extremely small. Even the galactic center, about which you will hear, has a size, and with 4 million solar masses, has a size of only 20 microarc seconds. That's about this much on the moon. So a normal telescope would not be able to resolve that. So that must be our first goal, to build telescopes which have high enough resolution. And we know, of course, the law of diffraction. If you have a lens there, then the angular resolution of that lens is proportional to the wavelength of measurement and inversely proportional to the size. So build a big telescope and then, you have the resolution. No, that's not that simple. Because if you have looked in the dark night out there, you see the stars are flimmering. And that flimmering is called seeing. And that you have to overcome, and I'll tell you how we do this. But then actually it's interesting that all the experiments which I mentioned to you, the optical work or optical near-infrared work, the gravitational waves and the radio waves, all essentially work with the same technology. And that's a technology which was invented by Michelson and Morley and Young, and that's interferometry. So you take here, in this case, 4 mirrors, and you let the light combine from these 4 mirrors, then you get interference. You get these interference fringes, as we call it, and they are spaced, the narrower, the wider the mirrors are apart. So actually, Michelson in 1920 put 4 such mirrors on top of the 180-inch on Mount Wilson. You see it there, and looked at distant stars. And he was actually able, for the first time then, to do interferometry in the optical and resolve the sizes of stars. That was a sensation then, but that was Michelson. Nobody else could really repeat this for a long time. Charlie Towns was the second one, but then it took until only about 10, 15 years ago until the interferometry in the short wavelengths is possible. Okay, the radio interferometry I already mentioned, and the current leading device is called the Event Horizon Telescope, as I said, with telescopes spanning the entire globe. And the gravitational wave people, use interferometers just like that. LIGO, Virgo, Kaga. And with that, they have been able to look at masses which move around each other and then, in the end, actually produce a black hole. Now, the machine which we have actually worked with in the last years is this one here. It's Europe's large 4 times 8 meter telescope, VLT, on a mountain in Chile, in the Atacama Desert. And you see these wonderful telescopes, beautiful skies there, and we have been able to actually combine the light of these telescopes and get very high resolution out of them. Last night, we for the first time did the following experiment. We took from these 4 telescopes and sent 4 laser beams into space. Now those laser beams are focused at about 100 kilometers in the upper atmosphere. There, they create what we know as a laser star, which is then reflected backwards into the telescope. And that we use to compensate the vibrations of the Earth's atmosphere. It's a very complicated technique. This technique has been in the working for about 30 years, and I have to say, I'm extremely proud about the European consortium which has been able to do this, and to get from that indeed images which is so good as for sure the 8-meter telescopes themselves, but we get even further. We can use these 4 telescopes in an interferometer to get the resolution of the size of the interferometer. So that's a 200-meter telescope. 200-meter telescope. So that's extremely good. So here is our first target, the galactic center, because as we discussed, these quasars are too far away. At least at that time, back then it was too far. Not anymore, it turns out. But the galactic center is so close. But there's a problem. When you look up in the sky, in the southern sky in particular, you see the wonderful plane of the Milky Way at night. But where the galactic center is, it's a dirty black. You see this stuff. That stuff is interstellar material, interstellar dust. And that interstellar dust basically, weakens the short wavelength light, in particular the optical. Optical doesn't even make it to us from the galactic center. But with the technique of adaptive optics, we can actually then go to high resolution, and we see the center of our galaxy. Many, many stars there. Millions of stars. 1 million times higher density of stars than we have it around us. Also very massive stars. There's also this green thing is a radio source, which is very bright and very compact. So this is the center, we believe, of our galaxy. And so in the 1980s, first Charles Towns and his group, when I was one of the postdocs, and then later on, we and also Andrea Guess at UCLA used the technique of adaptive optics and so forth to get ever better imagery of the central region. That's interesting. That's called flying into a black hole. Yeah, well, time goes backwards then, it's very clear. Okay, let's go back where time was. Okay, so that's the galactic center, and there is that picture. And the idea was then, when we started this with the stars in about 1990, and the first detectors which were good enough in the infrared to measure the positions of those stars and then measure them again and again and again for years, for many years. Both groups measured for 30 years until they had a solid result of the motions of the stars. There they are. Here you can see for a few of the stars we are tracking actually the orbits of the stars surrounding Sagittarius star, that radio source. So the radio source, as perhaps suspected, is the center of the Milky Way. There's only radio emission, not much optical emission, but obviously that could be it. And indeed, the motions of the stars when they come close to the radio source are enormous, about 8,000 kilometers per second, 100 times as fast as the Earth around the sun, or more. Here you see the data set in 1 year, 21, how we actually can see within a given year the motions of these stars around Sagittarius star, which is one of the points there in the center. And indeed, the velocity is about 8,000 kilometers per second, and that tells you something about the strength of gravity. Okay, so that is sort of the technique we're using, and then you have to have patience. And we have a very, very good team since over all these years to improve the equipment and get ever better images. I'm sorry with my fingers here, I'm doing a mess. So for this particular star here, S2, we have been able to put together a complete orbit. It takes 16 years for the star to go around. And we can see when it's close to Sagittarius A star, at a distance of about 15 light hours only, that it moves from day to day, not year to year, from day to day. And we are beginning to see the first effects of general relativity. So for instance, as you see in the bottom right there, we see that relative to Newton, where you would not expect any change in the wavelength of a line due to the mass, that when the star comes close, and that's in the center there, it's shifted to the red, so positive velocities. And general relativity is the red curve, and the data are the green symbols. So you can see we can, in a sense, quantitatively now go ahead and test not only is there a mass there, but is the mass and the effects we see of that mass consistent with general relativity to the detail. And that is really what we should do as scientists. Now, the stars move at about 1,000 times the event horizon size, so that's still fairly large. But we can also go closer. Sometimes there are little flares, probably magnetic effects on the surface of Sagittarius star. And when they occur, it's polarized emission from very hot gas, and then that gas starts to orbit at about 1/3 the speed of light. And our radio colleagues see also the distortions, the lensing of the central source. And finally, in general relativity, if you have one massive object in the center and another one orbiting it, in Newton, if there's nothing else around, that orbit would always stay the same for all times. Not in general relativity. In general relativity, the orbit starts to precess in the plane of the motions that's up there. That's called the Schwarzschild precession. And also it processes if there is spin of the black hole around the black hole. So there are really very well predicted effects which we can measure. See, but down there below, you can see that compared to Newton, where we wouldn't have seen any deviations, we see what general relativity indeed expects. So the Schwarzschild precession has been seen. Now the next big step is spin. And sure enough, since last year, we have now discovered a star which comes 10 times closer than the star S2. It's only 100 Schwarzschild radii, and that allows us to probably see the spin in a few years. So all of these measurements, which I've shown you here in the galactic center, radio, near-infrared, etc., have given us a mass distribution as a function of radius and show that that is equal to a constant point mass of about 4 million solar masses. So if you now ask the question, is that really a black hole? Then you can compare it to this diagram where a black hole is on the very left side. And all other possibilities which our theoretical friends have come up with, like conglomerates of dark matter, fermion balls, boson stars, and etc., are a little further out, not much, but a little further out. And indeed, already now we can exclude fermion balls and almost also the boson stars. In the next generation with the big telescope ELT and also the EHT, we hope to exclude boson stars for sure. And then finally, when I'm probably already under the table, gravitational waves in space with the ELISA mission will be able to see the in-spiral of a stellar black hole into a big black hole, and that will give us the accuracy to say that all of these other things are wrong. But you see, if you follow me, this takes time. Sometimes there are discoveries which you make in one afternoon. Sometimes the discovery takes 50 years, or in this case, 100 years. But I hope you follow me. We, as humanity, are curious. That is our key feature. We want to know, not to hear in social media or from President Trump. No, we want to know, and for that we have to have sometimes real patience to go with it, build ever better equipment, think ever harder, have better computers, and then find the truth. And I hope the young people here have that courage to take on this long road which you need. Now, let's go a little further out. So I've talked about the galactic center, but then in the meantime, many other objects astronomers have found in nearby galaxies that may very well be also black holes. You can't know, but it looks pretty like they are. And the interesting thing is when you plot in the vertical scale the mass of these central objects versus the mass of the center of the galaxy, the bulge mass, these are these green points. You see they're sort of a little correlated. Not super correlated, but you know, there's a scattery correlation. And that scattery correlation, everyone believes, has to do with the evolution. The black holes and the galaxies form together. And Simon White will tell you more about this. That is a feature of what we know about our universe and how our universe on very large scales formed structure. And then over time, the galaxies which formed grew in mass because they acquired ever more material from the outside. And maybe that also then led to the formation of black holes. And indeed, for the nearby galaxies, the ratio of that black hole or dark central mass to the bulge mass is about constant. This is what I said. It's likely a correlation. But here's one issue. When you calculate how fast they are growing in the local universe, then the mass doubling time scale is 400 megayears, 400 million years. Sounds like a long time, doesn't it? But actually, in the universe, it's not. Excepting at very high redshift, 13 billion years ago, there shouldn't be any black holes close to that because they wouldn't have had time. And sometimes you really experience surprises. The James Webb Telescope has all of a sudden discovered pretty big black holes already about a gigayear or even a few hundred megayears after the Big Bang. And we are puzzled. We are puzzled how that could be. Are there different ways of forming black holes? Now, of course, first off, we have to show that these objects which we have identified are black holes, like in the galactic center. That seemed like a joke, impossible 20 years ago, but it is not anymore. Because the supermassive black holes here often are surrounded by a very hot region, a so-called broadline region, which moves with a speed which is given by the size of the broadline region and the mass of the central object. And so we can actually, with the interferometer, see that rotation. And from the rotation and the size, we get a mass. And so we can measure actually the masses of distant quasars. There it goes. Here we're flying, in our spaceship at speed of light through the solar system, away outside of the Milky Way. And finally, after 12 billion years, there's the Milky Way, other galaxies surrounding. We're still traveling and traveling and traveling. And finally, there's one of these active galactic nuclei with a broadline region and a black hole. And so what we do is we take spectra with the interferometer of this rotating disk there, and when the light from that active galactic nucleus travels back all the way the way we just came, then we can, in our instrument, the interferometer, actually resolve it and see how the red and the blue parts of the spectrum are separated. Now, this is fairly superb technology, and it took us about 25 years to get there, but we are now there that we see these patterns, which are due to the rotation of a broadline region. See, that's the pattern, and then you put it onto the spectra, and there it is. And that's our inference for a distant quasar. So this is what I mentioned to you. We now are able to measure what are probably black holes at 1 to 2 gigayears after the Big Bang. So while in the local universe, these red points gave us this correlation which I showed you before, when you go very close to the Big Bang, the new measurements, both with JWST and also with our instrument, show sometimes very much bigger masses of black holes relative to the central mass. So the question is, what does that mean? Do they grow faster? And if so, why? Is there so-called super-Eddington accretion? Are there other types of star clusters which gave an advantage? Or, and that has been speculated in the last few years, very much so by the particle physicists, are there already black holes formed in the Big Bang? You see, there is almost an infinite possibility of questions. You young people, the sky is open for you to study and study the in-spirals, which I mentioned already, measure the black hole masses through gravitational waves, or to interferometry, as I mentioned to you. So in the future, we have so many fantastic machines. The James Webb Telescope now, and hopefully for some time, in about 3 years, we will have a 40-meter optical telescope in the Atacama Desert. Then this mission LISA in space, which I mentioned to you already, measuring the in-spiral of a black hole into a big black hole. This is going to be incredibly exciting, incredibly exciting. Thank you.
Thank you. Thank you, Professor Genzel, for such inspiring and really interesting presentation for our audience. Now we'll open the floor for questions. So if you have any questions, please feel free to put up your hand, and our staff members will be bringing a mic over to you. Any questions from the floor? We'll also open the question and answer session to our online audience as well. So please feel free to type out your questions at the Q&A box. Okay, we have one gentleman here at the front.
Thank you, Professor. My name is Jeff, techchannel.uk. Yesterday, I already asked you one question about the general development of the astrophysics in China and US. I want to follow up. Would you give some advice to like the Hong Kong government, the Chinese government, how the two places can improve their technological developments, and in general, not only in physics, across different technologies?
Yeah. Thank you for the question. Well, okay, I'm not the sphinx of all these questions, but it's pretty obvious that astrophysics now is one of the most active and interesting parts of physical research, physics research. That was different 40 years ago when I started. My father, who was a physicist, did not think that astronomy was all that interesting. But that has changed, and the reasons are obvious. We can get at issues and problems with our technology now, which were absolutely hopeless back then. Can that go on? And there we have to be doubtful, because the machines which we have already seen now, like the James Webb Telescope, that is at the absolute limit of what the United States of America has, and I believe will, be able to put into basic research. We're very, very lucky to have it. It almost died 3 or 4 times on its way, but then we have it. In Europe, we have had, I think, the one clever thing coming from the war, which is we've learned to work together and have international collaboration and not try every nation for itself to do this, because you could have never done anything. And all the great things we can do now, like these telescopes in the Atacama Desert, or also the European Space Agency, is due to collaboration. I know, and I told you yesterday, I'm absolutely full of admiration for the progress in this region and country. It's absolutely fantastic to see the vigor and interest of the young people to get themselves active in this region. That is your asset, number one. Your asset number two, of course, is if you have a government which is willing to support it. Well, that's a fundamental thing. But will they be willing to support for a very long time a sustained effort which will be needed to ask some of the difficult questions? So that is something you have to build up a structure that can make that case. And then, of course, the question is, how about worldwide collaboration? We've tried this now in some cases, not always easy, because if the political and structural interests of the partners are too far apart from each other, it's very difficult to make decisions. Of course, China will and can move forward. The big fast telescope is already one example, and the space experiments are already very, very impressive. But let me just congratulate you in China and in Hong Kong for making that step, because it's really fantastic for me. I've been coming here to Honolulu, to Hong Kong for well, I've been also in Honolulu, but to Hong Kong for 20 years, and I think it's just breathtaking.
It is our honor to have you at the forum as well. So we have another question from our audience.
Hello, thank you so much for your talk. My name is Rafael Asso, and I'm a biochemist at the University of Toronto studying Parkinson's. And so I'm obviously looking at your talk from a very biochemist point of view, and I'm always thinking about biosafety and how to keep researchers safe. So, if one of us ever encountered that mini black hole as shown in your final film, sorry, I'm trying not to laugh myself, but how do you recommend, what are the safety measures in terms of interacting with black holes? Should we be interacting with black holes? And finally, who do we call if we ever find a black hole? Thank you.
Yeah. I can calm you down. The problem of an encounter with a black hole is not very likely, for any given time. But let me give you an example where we humans actually have escaped deaths, at a far better way than we would have thought, and that's the Apollo mission. In retrospect, one has looked at the time occurrence of the Apollo missions and the occurrence of solar flares. And there was in particular one, I believe, of the Apollo missions where a solar flare occurred within a day of the end of the mission, I believe. Had that flare occurred then, the astronauts would have been dead. Absolutely clear and dead. So in that sense, let me say, I personally am not, and that is, of course, every country's and every region's decision, count on manned spaceflight. That is something which, maybe we leave it to Musk and so forth. But I think we can do unmanned probes equally good to do the difficult questions. We don't need to have people up there.
Okay, there's one more gentleman over there.
Hi there. Good morning, Professor. So thank you so much for your very interesting talk this morning. Really enjoyed it. My name is Adolphus. I'm from Singapore. I work on risk science and uncertainty quantification. And I look at your presentation and I just recall many years ago I was working on the microsat interferometer, and my mates and I, we took about days just to calibrate the system so it's precise enough to generate the interference pattern. And I was just beginning to wonder, for a large-scale setup like what you just showed, and there that shot up 4 lasers, and you're able to obtain some patterns with high degree of precision, and it begins the question: how long did you actually take to calibrate, everything so that in this large scale it is able to produce such wonderful pattern? Thank you.
Well, the first laser star was generated in the United States as part of the military research. It was not used for very much astronomy, but then in Europe we started in the early 90s. We had the first sodium laser star going in about 93, okay? Then ESO, the European Southern Observatory, gave us the green light for the first big machine. And since then, many telescopes on the Earth have used that technology. However, what I've shown you today is indeed the first time we use it for 4 telescopes at the same time, and thereby, make such a high resolution possible for distant telescopes. And we are dreaming, and maybe that's where international collaboration could come in to make an interferometer with baselines of 1, 10, 100 kilometers. That would give us resolutions this big near the Big Bang, okay?
Any other questions from the audience? There's one more.
Good morning, Professor. I'm a researcher from Tsinghua University, and what do you think of the biggest opportunity to make discoveries about deep learning in the planetary science? Okay, thank you.
I didn't get the question, sorry.
Deep learning means artificial intelligence.
Deep
Well,
learning.
artificial intelligence and intelligent learning and so forth in computers is something astronomers have been using actually for a long time, okay? It's not so surprising for us, especially the theoretical astronomers, Simon Yu, and have been using code which comes close to this, and we are using it, of course, for our big machines. But the question often is, of course, will artificial intelligence actually allow us to do something we could not as human beings do? As a helper, yes. I'm skeptical that artificial intelligence will, so to speak, come up with something which we couldn't do. But who am I? I'm an old man. Maybe we will be surprised. Simon, do you have an answer?
Thank you, Professor Genzel, for responding to this question. Any other questions from the floor? There's one more gentleman just put up his hand.
Good morning, Professor Genzel. Thank you very much for your interesting presentation. I'm Adrian. I am an astrophysicist at the University of Cambridge, working on analyzing gravitational waves emitted by black holes. So I consider myself half a black hole physicist, but one difficulties that I encounter is how to explain to the general public why we should care about black holes. So would you have any advice about when I try to popularize or explain my work to the general public, how I should proceed? Of course, I guess you won't just show the public the last movie that you have just shown, right? Thank you.
Thank you for the question. Okay, well, I'm not almighty in my knowledge, but it is certainly the case that I'm giving many, many talks per year, about 40, 50 talks, and 30 to schools, and I can tell you, the younger the better. Yeah, I mean, the young people, 10 to 15, even 7 to 15, you know, they love it to hear all of this. They may not understand everything, but they love to hear it. And in this curiosity, that's what makes, as I said, that's what makes us human. And you have to be curious because you have to do something difficult. And difficult means you have to put your mind and perhaps your fingers and whatever else to it for a long time. From nothing comes nothing, okay? No lunch out of, thin air.
Yes, we have one laureate right there that would like to share a few words. May we have? Thank you.
Well, from your challenge, a couple of thoughts spring to mind about artificial intelligence and what we can learn from it. Because as we all know, everyone is thinking about this and all the things that we see, magic that seems to come from ChatGPT and large language models. And the first thing which springs to my mind is large language models summarize all the data which they can put together and analyze. And so they're summarizing for us in some way the sum of human knowledge as written. And that includes the correct results and also all the rubbish. And what you get back is a summary of everything, and it takes considerable judgment to decide what is rubbish and what is there. So there's an enormous danger in taking what you get back from the language directly. The second thing is, which I think is a deeper thing, is that we're talking about new knowledge. And we don't really understand where scientific insight comes from or any other kind of human insight, but it seems to be a capability of the human species to generate what we at least perceive as new knowledge. And I don't think you can get that from a large language model. So maybe the most important part of scientific research can never come from this kind of algorithm.
Thank you, Simon. I think that's very helpful. We had every year there's the conference of the Nobel laureates in Lindau in southern Germany. And 2 years ago, we had 35 laureates on stage. And the question was, do you believe that artificial intelligence will give us a major new insight and discovery? And I would say out of the 35, about 10 said yes. The rest have said no. Your judgment. I mean, it's a guess. There are extreme dangers, you all know, politically. And there's the extreme difficulty for young people. how do we old ones, if you want to judge your work, do this if you give us a application written by ChatGPT? Silence. Okay, thank you.
Thank you so much. We have time for 2 more questions. So let's see if anyone would like to exchange your ideas with Professor Genzel. There is one participant.
Thank you for a nice talk. I was wondering, at the beginning of your work, how did you, make sure this is the galactic center? How pinpoint the galactic center?
Yeah, no, I think that's a very fair question. In fact, I should tell you that there is no point that is the galactic center, because the black hole mass, which 4.3 million solar masses, is embedded in the galaxy. So in a way, it sits in a position which is part of the gravitational interaction with the entire galaxy. So we can compute that on average, that 4 million solar mass will, move around stochastically at about 2 centimeters per second. Not that we can easily measure this, but no. But this is not the question the answer to your question. I mean, the idea that it might be the radio source came on very, very early on. Okay. And was confirmed by a number of the properties of the radio source. Also, in comparison to other active galactic nuclei, where there's also the radio emission is sort of a signal, so also some X-ray emission. So this is sort of a signal that this might be the region you might want to look for. But then, as we were beginning to measure gravity, then it became clear.
All right, any other questions from the floor? Yes, there is one young man over there.
Hi, this is Anthony Chan, specializes in computational imaging and super resolutions. I also attend a separate tenure-track lecture by Professor Katie Bowman in Caltech, who's also happened to be a major player in the Event Horizon Telescope. A question is more about the hidden figures behind all the international collaboration for investigating black hole and visualizing the
Sorry, I did not get what is it?
My question is about hidden figures and visibility as an engineer and in a PhD. So not a lot I heard about the stories about the Western digital hard drives, 25 petabytes flown daily from the telescope site to the Max Planck Institute, and they are helium filled. With all this technological breakthrough and scientific challenges in order to support a single figure in the astrophysics journals. As a PhD in engineering, what's your advice to them to gain more visibility and to write about their own stories in the international collaboration, especially in the Event Horizon Telescope scale program? Thank you.
I'm sorry, I failed the test. I don't understand what your question is.
I think the keywords from his questions were hidden figures and visibility. Am I correct?
Pretty much, yes. That's excuse my strong accent here. Thank you.
The visibility of
as an engineer, PhDs. Right. The hard drives were helium filled and fly daily from the Event Horizon Telescope to the Max Planck Institute for follow-up data analysis. And these are all the engineering charges that deserve a team of PhDs there. But they don't write papers, right? Thank you.
Yeah, well, okay. I mean, I think in our experiment, we, of course, have also a large team overall, maybe if you count ESO and the other countries, maybe 150 people. But we are an integrated team, so the engineers are on the scientific publications as well as the scientists. We don't make any difference there. Okay. Now that is also disputed by some of our colleagues because it makes these huge lists of publications. But I have grown up under the tutelage of Charles Towns to have the greatest respect for engineers and what they do. Okay, without them, we couldn't build what we build. Okay, and so in that sense, the visibility has to also be given to them, and the triumph has to be given to them. I showed you this measurement with the 4 lasers 2 nights ago, and yesterday at noontime, Hong Kong time, my computer started exploding as the entire team and ESO started jubilating and congratulating each other. Now the Event Horizon team is a more difficult thing. I cannot understand it in detail. It has some features which I'm a little uncertain about how they are doing it and what they are doing. They're not a oneness as I think you might try to be.
Thank you. And one last question from the audience, please. Yes, there's one.
Hello, my name is Zishan. I'm a PhD student studying galaxy evolution. So my question is also about how to communicate our field to the general public. I think you made a great comment about when you talk to the young students, like they are very curious. But I'm trying to ask him from the other angle. What about those older people? They probably in the position of power. They are kind of like the funding source to our research. They could be government officials. They could be private donors such as real estate developer. So how do we convince them our research about black holes are important to helping the countries to develop?
Well, okay, look, I have as a European, as a German, the advantage that I don't have to fight for donors as I would have to do in Berkeley. But my wife is sitting there. She's a pediatrician, and so she has managed several times to hook me up with her PhDs and her doctors. And I thought they were very interested too, weren't they? They were. I don't think it's just a question of how you do it. I often use music, actually, as a sort of continuation. And of course, if you come and explain dry formulas, that's hard on everyone. But if you make it fun, I mean, then people like it. Yeah? And the kids have the advantage that they still do this.
Maybe you can create a very interesting presentation to convince your future donor when he's very young. All right, thank you very much, Professor Genzel. Let's put your hands together to thank Professor Genzel for all the inspiring presentation and all the insights that she has provided. Thank you. We're truly honored to have Professor Genzel with us at the forum and be inspired by his presentations. And I'm sure we all look forward to further interact and exchange more ideas with Professor Genzel in the coming days. So now, ladies and gentlemen, we'll have a 20-minute coffee break. Refreshments are available at the back of the hall. Please be returned at the hall before 11 a.m. for our panel discussion later on. And we'll see you later. Thank you.